Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will tell you our lecture on theory of numbers, lecture number 45, in which I will solve some problems on order of an integer modulo m. Now we solve a problem. Problem is given that integer a has order 3 modulo p, where p is an odd prime number. Then so that a plus 1 must have order 6 modulo p. Now we solve this. Given that order of a modulo p equal to 3, that this is number 1. Therefore, a and p are positive integers such that GCD of a and p equal to 1. Also, given that p is an odd prime, from 1 a cube is congruent to 1 modulo p, where 3 is the least positive integer. To fulfill two implies that p divides a cube minus 1, implies that p divides a minus 1, a square plus a plus 1, implies that p divides a minus 1 or p divides a square plus a plus 1. Let this is number 3 and this is number 4. From 3, a is congruent to 1 modulo p, implies that a to the power 1 is congruent to 1 modulo p, implies that order of a modulo p equal to 1. Therefore, 1 and 5 contradict with each other. In 1, order of a modulo p is 3. Here in 5, order of a modulo p is 1. Already this is given. Order of a modulo p is 3. So 5 is not possible. Hence P divides a square plus a plus 1. Only 4 exist. Implies that a square plus a plus 1 is congruent to 0 modulo p. This means we have no remainder. Remainder is 0. This is number 6. Implies that a square plus 2a plus 1 minus a is congruent to 0 modulo p. Implies that a plus 1 whole square is congruent to a modulo p. Multiplying both sides by a plus 1. Here we get a plus 1 whole cube is congruent to a multiply a plus 1 modulo p. Implies that a plus 1 whole cube is congruent to a square plus a modulo p. Implies that a plus 1 whole cube is congruent to a square plus a plus 1 minus 1 modulo p. This is number 7. 6 may be written as, here we may write 0 in left side and a square plus a plus 1 in right side. 0 is congruent to a square plus a plus 1 modulo p. This is number 8. Subtracting 8 from 7, we get a plus 1 whole cube is congruent to minus 1 modulo p. Implies that if we take square in both sides, then in left side we get a plus 1 whole to the power 6 is congruent to minus 1 whole square modulo p. Implies that a plus 1 whole to the power 6 is congruent to 1 modulo p. Therefore, order of a plus 1 modulo p equal to 6. Our problem is solved. Now we solve the next problem. Let order of a modulo m equal to n, then for k belongs to capital N be the set of natural numbers, such that a to the power k is congruent to 1 modulo m, double implication, n divides k. Given that order of a modulo m equal to n, therefore a and m are positive integers with GCD of A and M equal to 1. Let this is number 1. From 1, A to the power N is congruent to 1 modulo M. N be the least positive integer. Let this is number 2. Now let K belongs to N, capital N be the set of natural numbers, and A to the power K is congruent to 1 modulo M. Let this is number 3. From 2 and 3, we get here A to the power N is congruent to 1 modulo M. Here A to the power K is congruent to 1 modulo M. But N be the least positive integer. Therefore, N is less than equal to K. This is number 4. From 4, we get N equal to K or N is less than K. This is number 5 and this is number 6. From 5, we get N divides K. By using division algorithm in 6, we get K equal to NQ plus R. Q and R are integers and R is greater than equal to 0, less than N. Let this is number 7. Using 7 in theory, we get A to the power NQ plus R is congruent to 1 modulo M. Implies that A to the power NQ multiply A to the power R is congruent to 1 modulo M. Let this is number 8. Raising power Q in both sides of 2. A to the power NQ is congruent to 1 modulo M. This is number 9. Multiplying both sides of 9 by A to the power R, we get A to the power NQ multiply A to the power R is congruent to A to the power R modulo M. Let this is number 10. From 8 and 10 we get here in 8 in left side we see a to the power n cube multiply a to the power r. Also in 10 the same value. Therefore a to the power r is congruent to 1 modulo m. This is number 11. Since we know that a to the power n is congruent to 1 modulo m, n is the least positive integer. Therefore, from 11 we get r is greater than n. This is number 12. From 7 and 12 we get a contradiction. Therefore 11 is possible only when r equal to 0. This is number 13. Using 13 in 7 we get k equal to n cube plus r equal to 0 implies that k equal to n cube implies that n divides k. Proved. Conversely, let n divides k. This is number 14. Since we have order of a modulo m equal to n implies that a to the power n is congruent to 1 modulo m, n be the least positive integer. This is number 15. From 14 k equal to n cube. Q is an integer. Let this is number 16. Raising power q in both sides of 15. We get a to the power n cube is congruent to 1 to the power q modulo m, implies that a to the power n cube equal to k is congruent to 1 modulo m. using 16. Proved. Now we solve the next problem. Problem is, if GCD of A and M equal to 1, then order of A modulo M divides phi M. Phi M be the Euler's phi function of M. That is, order of A modulo M divides phi M. Now we solve this. Let order of A modulo M equal to n. N be the least positive integer. This is number 1. Phi M equal to Euler's phi function. We know that order of A modulo M is less than equal to phi M. Let this is number 2. Also we know that if A to the power k is congruent to 1 modulo M, then n divides k. This is number 3. Since phi M is greater than equal to n, therefore we may take value of k equal to phi M. This is number 4. From 3 and 4 we get n divides phi M, implies that n be the order of A modulo M divides phi M. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.